Hello and welcome to my talk. Today I'm going to talk about my journey from provisioner to Terraform provider, integrating Kustomize into Terraform and the cubestack framework. I'm maintaining an open source Terraform framework called cubestack. And when I say framework, I mean that in the exact same sense as Spring Boot is a Java framework. Right? Just like this, cubestack is a Terraform framework. And similarly, just like Spring Boot aims to provide the best developer experience for building microservices in Java, cubestack aims to provide the best developer experience for building Kubernetes-based platforms using Terraform. As many of you will know, a Kubernetes-based platform will always consist of both cluster infrastructure resources as well as what I call cluster services. So services that need to be running on the cluster before you can deploy application workloads. Examples of this are monitoring daemons, log forwarders, service mesh, ingress controllers, policy enforcement, all these kind of things. And I believe in order to have a robust workflow, it's important that you can promote both cluster infrastructure and cluster services through these environments simultaneously. And so with the cubestack framework, any change starts in the review process. Review means you send a pull request and ask for a peer review. And for the peer review, you have the code changes to review as a team. And additionally, you get a Terraform plan. What changes Terraform would do to the ops environment if you were to merge this into main. If you actually merge this into main eventually, Terraform will run an apply against the ops environment to validate that the changes do apply correctly against real cloud infrastructure and Kubernetes resources. From there, depending on how you configured the framework and how many environments you chose, you can promote that exact same change into the next environment and possibly the next environment. So on the slide here, I have two environments that run application workloads, one called apps, which you could use to run only dev and staging application workloads, for example, and then one called apps prod, where you would run production application workloads. And just like you can configure one Kubernetes cluster and its cluster services in each environment, you can also have multiple clusters, either for multi-cloud or multi-region setup, or because you want to have different clusters per team in the organization, or something like this. So the first implementation, in order to be able to have cluster infrastructure and cluster services moving through the environments together, was a provisioner-based approach. If we go back 2 years to February 2019, this is how the integration looked back then. We would have two data sources, one customized build data source, which basically was given a path to a customization and then would run customized build and write the output to a file in a specific location, and a data source template file that would be used to generate a kubeconfig that we can later use when we kubectl apply the resources that the customized build has written to that file. After the two data sources, we would have a null resource with a local exec provisioner that runs kubectl apply with the file that we generated in the external data source and would be using the kubeconfig that the data template created for us to apply that to the correct cluster. Additionally, the customized build external data source also returned a checksum, and we would store that checksum as a trigger in order to only run kubectl apply if Kubernetes resources changed. So taking a look at the provisioner approach, what was good about it is that we did get a unified lifecycle for both cluster infrastructure and cluster services, so we could move them through the environments together. And the Kubernetes resources would only also be applied and only show up as a change if there was a difference. However, if we ran Terraform plan, diff that was shown wasn't actually any useful because we would just see that some hash changed from one string to another string, and it wouldn't show us what the changes to the Kubernetes resources would be. And similarly, the apply wasn't fully integrated into Terraform, but instead Terraform would shell out to kubectl, and kubectl would run the apply. So the individual resources are unknown to Terraform, and from Terraform's perspective, either the kubectl apply succeeded or failed as a whole. That some resources would maybe be applied correctly and others would not, was basically outside of the state of Terraform. Working with this for a while, I realized that I wanted better integration. I would have to write a provider for this. So providers are written in Golang, never written Golang. I had a lot of questions. Let's just say I had a lot of questions. The only thing I ever, let's not say written, let's say copy pasted in Go was the Hello World example from the Golang website. Coming from Python, types and structs and interfaces and most of the Golang syntax were like entirely alien to me. And at the same time, while trying to learn this new programming language, I also had to understand how the Terraform SDK works. And so I was at a point where there was just too many unknowns, right? I didn't know the language properly. I didn't understand the SDK I had to use properly. And I didn't also necessarily really know yet what kind of provider I wanted to build, right? Does it need data source? Does it need resources? What schema is it going to have? Thankfully, Alex was so kind to answer a lot of my questions in the beginning, and I want to take this as an opportunity to just say thank you for that. All right, and so it put me into a position where I knew roughly where I wanted to go. So I could start experimenting, moving into that direction. So what I ended up with back in the day was that I would have one data source that would run the customized build. This replaces the data external data source we had earlier. I would give it a path to a customization that's defined somewhere on disk. And the second thing I would have is a resource called customization resource here, which using for each, I would be looping through the first attribute the data source returns, which is a set of IDs. And then the customization resource expects manifest in form of a JSON string. So this is the second attribute that the data source returns. Is manifest is a hash map where the keys are the IDs from the ID set, and the value is a Kubernetes manifest as a JSON string as it got generated by the customization build data source. So this way you could point the data source at any customization you would have. It would run a customized build, and then you could loop over the resources using for each in the customization resource and have them applied against the Kubernetes cluster to also be tracked in Terraform state. So if we compare this provider approach now, we still have the unified lifecycle, and also the Kubernetes resources only apply if there is a change. But the improvement over the provisioner approach here is that the diffs now show the actual changes to the Kubernetes resources. They show a diff of the JSON, and applies are fully integrated into Terraform. Each resource is individually tracked in Terraform state, and Terraform would know individually about each resource if the apply failed or if it succeeded. Now, of course, it was not as easy as the previous slides may make it sound, because there were a number of challenges I had to overcome to get the provider to the point where it is now. And I want to talk a little bit about them. So the first one I want to talk about is what I call the create namespace race condition here. So as you are probably familiar, Kubernetes resources may depend on other Kubernetes resources. So for example, namespace resources like config maps or deployments need the namespace to exist before you can create the config map. And similarly, if you create any custom resources, the custom resource definition has to be sent to the Kubernetes API server first. Otherwise, the API endpoints don't even exist. Unfortunately, though, Terraform providers have no access to the dependency graph. So while I had a list of Kubernetes resources, I had no way of telling Terraform that there are dependencies between these resources. What I did as a first measure is I probably abused wait for state. So usually, if you've ever run Terraform apply, you've seen these, there will be log message that says still creating, and then an amount of time and still creating, and a slightly higher amount of time, as Terraform has sent a create request and is waiting for the resource to provision. And that's what wait for state is usually used for. So you call it after the create, and you configure it to do a get request of some sorts against the upstream API to figure out if the resource has successfully been created before Terraform continues. So because I can only create a Kubernetes resource that's namespaced if the namespace exists. What I basically do is, before I even try to create a resource, I use wait for state to have that create loop until the namespace is created, and only then I do send the actual create request. I also do the same thing for custom resource definitions. I just don't have it on the slide here. If you want to see the entire code, the resource customization.go down there is a link so you can see the code on GitHub. And so I have this slide where I try to explain the race condition that can happen now. So first thing, by default, Terraform will do 10 resource operations in parallel. There's the parallelism command line argument where you can change that number, but by default it's 10. Assuming on the very left here, we have 11 resources, 10 of which are namespaced, and the first one is the namespace. If the namespace gets created first, all the other resources are applied correctly without problem. As long as the namespace is somewhere within those first 10 resources, like for example in the middle here, waiting for the namespace to be created by having those other resources loop using wait for state does do the trick. However, and that's the race condition, it can happen that for some reason Terraform selects 10 namespace resources as the first 10 resources. So all of them will start looping until the default timeout for that loop, or the default number of retries for that loop. And then depending on how far apart they started looping, as soon as the first one fails, the namespace will get created. Namespace creations usually are very quick, so it may still happen that some of the later resources will still apply correctly, but at least one, usually between 1 and 3 or 4 of those resources, would actually fail to apply, and you have to run Terraform apply again to also apply them. So that's the race condition that could happen because of this looping hack that I implemented. And so I wanted to fix this, but I think I unfortunately went down the wrong rabbit hole for quite a while. So on this slide, I have a few code snippets that I copied from the SDK to talk them through. First one here is the list function of the set, which has the comment that the order of the returned elements is deterministic, given the same set. The order of this will always be the same. The way this is implemented is that sets seem to be a hash map. The value is hashed, and the hash is used as the key of the hash map. This makes sure that there is no duplicates. And then when the list is returned, entries are sorted by their key. Additionally, the SDK gives the ability to provide my own schema set function that determines what the key used in the hash map is going to be, and this is also the key it will be sorted by. So based on this, I came up with the theory that if I generate hashes in a way that namespaces and CRDs would always be at the beginning of the entries in the set, and all other resources would be further down the list, then the customization resource using for each would loop over the resources in the order that they are returned by the set, and then hopefully I would not face the race condition. So I already said that I probably went down this rabbit hole for way too long, and unfortunately it wasn't the right thing to do, or it wouldn't entirely solve the problem. So the first implementation I did in August 2020 for the function that generates these IDs. It did improve the situation in my testing. The race condition seemed to show up less frequent, but it would still show up. Looking into this further, I realized there was a bug in the function that I wrote to generate the hashes, where a hash could become larger than the max uint32 value. And the way I had implemented my hashing function was that I would try to generate my special hash here. And if it failed for any reason, I would simply continue using the default hash function came with the SDK. So my provider wouldn't crash in these cases, but the order of the resources in the set would not be what I actually aimed for. And so after I found the bug and I fixed the bug, it further decreased the frequency of the race condition, but again, it didn't fully prevent the race condition. And so again, a few months later, in 2021, February, I finally settled on a different solution. And so what I did is, instead of just returning a set of IDs, I now return IDs prio, which is a list of 3 sets. And then the Kubernetes resources are grouped into one of the 3 sets. The namespaces and custom resource definitions go into IDs prio 0. Validating webhooks and mutating webhooks go into IDs prio 2. And everything else goes into IDs prio 1. This is how you would use this, where previously you would have a single customization resource. We now have 3, P0, P1, and P2. P0 would loop through all the IDs in IDs prio 0, and then P1 would loop through all the IDs in IDs prio 1. And this is the trick here. Set and explicit depends on customization resource P0. And P2, the same thing, would loop through IDs prio 2. And set an explicit depends on customization resource P1. So this way, if you apply this now, I have an example output from an Nginx ingress controller here. Because of the explicit depends, first it would create all the P0 resources, which in this case is the namespace. And once the namespace is created, we continue with all the P1 resources. I shortened this here because there's a lot of them. They all get created after each other. And then finally, all the P2 resources get created. And the same, if you destroy this, it also does the correct order, just in reverse order. So P2 first, then P1, and finally P0. Okay, so the next thing I spent quite a while figuring out is how to handle immutable attributes correctly. Some attributes of Kubernetes resources are immutable. Example would be label selectors. This is something that Terraform already supports because it's common also for cloud resources. There are certain cloud resources that you cannot update in place, but you have to destroy them first and recreate a new one. And for this, Terraform schemata have attribute force new. And if you set this, whenever a particular attribute of your provider changes, Terraform will generate a destroy and recreate plan for that resource. I couldn't use it like this for my provider because, as you may remember, my provider has manifest, which is a JSON string, and I cannot recreate the resource every time anything in that JSON string changes. But instead, I have to decide based on attributes inside the JSON string. Doing this client-side would be extremely complicated. And so what I ended up doing is I'm using server-side dry runs. So the SDK has a function to determine the diff of a resource, and I call a server-side dry run inside that function and use the response I get to determine if I can update this resource in place, the default, or if I have to force new and have Terraform create a destroy and recreate plan. The benefit of the dry run is that it's much better validation if it's done server-side, because it can include more than just the static schema of a Kubernetes resource. One example would be that it would also run past admission controllers if they are supporting this correctly and if they're configured correctly. And in my case, what I was looking for is that if there is an immutable field that my patch is trying to change, I would be returned an error that would tell me that the field is immutable. So I have to determine between errors that are because of immutable fields and errors that are simply because something about the resource is invalid. This is the force new flag. You can set it on the schema, but you can also set it in as part of the resource diff function. And that's basically what I'm using. And it looks something like this. So in the first example here, I was under the assumption that force type field value invalid with this string message field is immutable would be what the Kubernetes resource returns. If there's any changes to immutable fields, and then I would call force new on manifest, and Terraform would therefore create a destroy and recreate plan. Shortly after, it turned out that stateful sets return a slightly different error if you try to change any of their fields that are immutable, which is most of them. And recently, there was a contribution on the repository that apparently storage classes also need a special case here. So if anybody knows a better way than writing special case if clauses into the provider, like I'm currently doing, I'd very much appreciate an issue or a pull request to let me know how to do this better. The link again is at the bottom of this slide, but nevertheless, this is how it's currently implemented. So let's take a look how this looks from a user's perspective. So I have here is a module that installs Nginx Ingress, and these modules, they allow in the configuration to use any customize attribute that you can use in a customization.yaml file. In this case, I'm using common labels. Common labels does is just like the name suggests, it adds a label to every single resource that's in the customization. If the resource has a label selector, the label is also added to the label selector. So let's assume I have applied this before and I'm now making a change. It's highlighted in green here. If I now run a Terraform plan for this, it would look something like this. So I'm using -- target here to only show the changes for the deployment, because otherwise it would simply be too many resources to show them on the slide here. I'm also excluding the diff of each resource. But what you see here is that the namespace will be updated in place, because that only adds the label. That's a change you can do in place. But the deployment, it would set the labels, but it would also set the label selector, and that's immutable. It's an immutable field, and therefore here you see plan that says the deployment must be replaced. Another topic that I spent quite a while on, not necessarily because it's complicated compared to the other ones, more because it requires me to support all the attributes that are supported in a customization YAML and translate it into a Terraform schema, are these dynamic overlays. You remember, initially the provider had one data source, customization build, and you gave it a path to a customization on disk that was defined as static YAML. The question is, how can you patch Kubernetes resources using values from Terraform? And because, for example, templates aren't yet written to disk in the plan phase, but data sources are executed in the plan phase, you couldn't simply use a Terraform template to add another file of some sorts to your customization on disk, because again, it wouldn't exist during plan, only during apply, but that's too late for this to work. And so to solve this, because it's a very valid use case that a lot of users very early on actually identified, I think after the first release of the provider already, I created a second data source called customization overlay. And here, instead of providing a path to an existing overlay or base or like any sort of customization on disk, you can specify any attribute that you can specify in the customization YAML as attributes of the data source. By defining the overlay or the customization in Terraform syntax, you automatically can use Terraform variables, attributes from other resources, all other kinds of references and Terraform functions, etc. So the example here, very easy example, I'm basically reserving an IP address, a Google Compute address here, and then I have my customization overlay data source that I point at the base for Nginx Ingress, and the base includes a service type load balancer. And what I'm doing here with patches is I'm patching the service type load balancer YAML that I get from the customized base so that it uses the IP address that the Google Compute address resource returns as the value for the load balancer IP. This way you can leave the upstream YAML untouched, don't have to make any changes to the YAML files, which makes it easier to update them whenever upstream makes a new release. But you can still customize the values of your Kubernetes resources using values coming from other Terraform resources or anywhere else that you can, for example, query them from in Terraform using a data source. Recently, based on the provider and especially provider's new dynamic overlays feature, I created cluster service modules, which I really think show all the benefits of this integration in a very nice way. The first benefit, and that comes directly from Kustomize, is the fact the upstream YAML is left untouched. This means the modules can be automatically updated by a CI/CD pipeline based on upstream releases, because the logic of updating the upstream YAML in the modules is basically delete what's there and overwrite it with the new YAML from upstream. We consume that untouched in the customized sense. But at the same time, the modules allow, or basically that's a benefit of the provider mainly. Customized provider allows to integrate the resources coming from YAML entirely into the Terraform plan apply lifecycle, while still allowing to customize them. And finally, with the modules, it gives a very nice, unified and convenient module-based developer experience, also to maintain the resources on Kubernetes. So here is another example of one of these cluster modules. We briefly saw the Nginx module earlier already. The module basically has a very straightforward default module usage. You inject providers. You'll mostly do this to be able to control which cluster the resources get applied on. So you would create a aliased customization provider that you, in cubestack's case, can configure from a kubeconfig output that comes out of the cluster module. And then you set a source, which the modules are available from a registry, and a version. And the version schema here is that the first part shows the upstream version, reflects the upstream version of the package. So in this case, it would install Prometheus operator 0.48.1. And then there's the packaging prefix -kubestack.0 in case an upstream version has to be repackaged for whatever reason. And then all these modules allow passing in the configuration. And again, the configuration can be any customized attribute, meaning you have a lot of flexibility to customize the upstream YAML any way that you require for your platform setup. Currently, there are modules for a number of services already on the catalog, and now that the provider has reached good maturity and the modules have proven themselves on a small scale, I'm looking into adding more really soon and basically expand the number of services that are available from the catalog. Last but not least, there's also a module that basically has the exact same usage as the catalog modules, but doesn't bundle any upstream YAML. And the idea behind this module is that you have a convenient way to use the same module kind of workflow, but with any kind of bespoke YAML that you may be maintaining maintaining yourself for whatever reason. You could, of course, instead of using this module, also use the provider's data sources and the customization resource manually, but the module has the benefit that it does the explicit depends on kind of setup for you out of the box, and it's less verbose using the module than doing it yourself by hand. But of course, both is possible, and the idea here is really that I maintain these as part of the cubestack framework, but they're just Terraform modules, just like the provider is just a Terraform provider. There's no reason why these cannot be used standalone as well. My perspective, which is largely focused on the integration between Terraform and Kubernetes. I think there's really two major points. If I had to make a wish, it would be those two. Number one is that dependencies between provider resources, where the provider is configured from another resource or module, aren't currently tracked very well. Especially, for example, if you have a Kubernetes resource, an EKS resource, for example, that gets destroyed and recreated, the Kubernetes resources that are configured on top of that cluster are not planned to be destroyed and recreated properly, especially after the destroy. They stay in the state, and then the next time when Terraform tries to refresh them, you can't find the provider credentials, and then the entire thing errors out on you. And you have to work with --target. That's kind of annoying because it kind of prevents Terraform from fully automating this. And the other aspect on my wish list is if any resource that uses for each has a dependency on any other resource or one of its attributes that is in this known after apply state, then for each Terraform will simply refuse to execute this, and you have to again run an apply with --target, focusing the dependency first to make sure that the attribute isn't in state known after apply anymore, and only then can use for each. So in my case with the data source, it would be nice if I could define, especially for the customization overlay, which of those customized attributes do have the risk of changing the number of resources, because most of them don't actually, especially patches don't, which means if I'm using a attribute from another resource that's known after apply as an input to any of the patches, I run into this error. If I had to make a wish, these two things would be great to improve Terraform towards better Kubernetes integration, in my opinion. Well, so that's my presentation for today. I hope you got a nice overview of the journey from provisioner to provider, kind of interesting challenges I had to solve along the way, and what the current state of the provider is. If anyone wants to chat, there is a #Cubestack channel on the Kubernetes Slack where you can find me and a couple of hundred other people who are interested in the framework. Everything is open source, of course. You can find all the repositories on GitHub for the provider, the modules, and also the framework itself that we discussed today. And if you want to support the effort, consider leaving us a GitHub star or two. Thank you very much.